One of the more interesting applications of calculus is how we can tie it back to elementary knowledge about algebra and produce some interesting approximations. So if we go and construct the tangent line approximation. So if we have some curve f of x, and we have some point c at x equals c, and then f of c here, we can form that tangent line, and we can use the point slope formula and rearrange it to have that this line will have these characteristics, that the slope of the line will be the f prime at c, right? Because the derivative is the slope of the tangent line. And then you'll have x minus c, that's sort of that point slope form. And then you'll have, usually it's sort of like y minus y1 equals mx minus x1. Well, in this case, y1 is the value of the function, and that x1 is just that c point. So we can rewrite this using the c. And the reason we like to do this is because this now gives us this equation of the line. Well, why would we want to do that? We'd want to do that because that line provides a surprisingly robust estimate of values close to c. So the reason why this might be of importance is that it can sometimes be very complicated to evaluate functions at multiple points, because like in a computer and whatnot, evaluating those points can be very, very expensive depending on the types of calls. For instance, trigonometric functions are very expensive in a computer relative to polynomial functions. They take longer to calculate. So if you have this equation here, what we can say is, well, if I want to move a little bit to the right, to this little, just the slight delta x here, then this line, the red line, is really close to the blue curve. It's within probably some amount of tolerance, maybe. So I can then say that the function for values close to c, I mean, you can't go super far, right? If you go this far, you diverge from the curve. But you can say that this line roughly approximates the function near c. So let's put this to practice with an actual example. If I have the function 1 plus sine of x, so trigonometric functions are expensive, so we don't like to compute them if we don't have to. We want to find values near x equals 0 for what this is. So if in this particular case, the c value that I'm evaluating is 0, because I'm looking for values near 0. I can find the value of the function at 0. If I plug in 0 here, I get 1 plus sine of 0, which is just 0. So the function value is 1. The derivative of this function is just cosine of x, and the value of the derivative at c, which is the value of it at 0, is cosine of 0, which is also 1. So there's a lot of 1's going on here. So this f of x, you have f prime of c, which is 1, x minus c, and c is 0, plus f of c, which is also 1. So what this tells me is that the function x plus 1, or you could write it as 1 plus x, because it's probably closer to that structure, that this function approximates 1 plus sine of x near 0. And we're going to plug in some values to see if that doesn't hold. Well, at 0, the function, or the tangent line is 1, the function is also 1, and the difference is 0. So there's no difference there. If I plug in 1/10, so I'm pretty close to 0 here, I get 1.1 for the function, because that's 1 plus 1/10. But if I do 1 plus sine of x, I don't quite get 1.1, I get 1.0998. So the difference is 0.0002. Pretty small, right? That's, let's see, 10 hundred thousandths. So it's 2 10,000ths of a difference, right? Not a lot of difference. However, if we move out to 1/2, 1 plus a half is 1.5. Now 1 plus sine of a half is 1.479, or 1.479, and the difference is 0.02. So we lost 2 digits of precision here by going out to 1/2. And that's not terribly bad. I mean, if you think about it, 0.02 is a pretty small difference. One thing a lot of times that is calculated, this is what's called an absolute difference. It's just the two numbers subtracted. But another thing that's common in real world scenarios is what's called a relative difference. So what happens is you take this number and you divide it by the real value, and you can see kind of how percentage wise far you are off. Now I didn't do that here, but that is a technique. And what we find is if we go in the negative direction, we get the exact type of behavior here, except in this case I overestimate it, in this case I underestimate it, but it's by the same amount. And that has to do with the fact that sine's an odd function, and so there you get this mirrored behavior. But anyway, it's a pretty interesting idea to use the tangent line approximation. And what you find is there's a lot of techniques that you'll get to as you start to study things like integration that use this type of setup to approximate integration on functions that would be kind of difficult to do manually.